Well, hello. This is the third time I've recorded this video, but this is Clint Guyman. I know God lives and loves us. Just wanted to talk you through using Aspen to simulate this condition here, where you have some liquid water flowing into a unit operation. This here is called a dryer, and dry air is flowing into there, and then a vapor phase exits with the liquid phase. So first we'll go to our Cadum machine and start Aspen. So Aspen Plus, start that up. And while it's started, I'll just talk about this unit operation event here a little bit. But you have a water carried in with the dry air, and in this case, we're simulating as if it's an equilibrium, where the water could be dispersed in fine particulates, for instance. It's an equilibrium scenario. So Aspen will start up and look like this as it starts, and then should open. And hold on here just a minute. Here we go. Here's some help that can be good to review. Close that and just do new simulation. When it opens the software package, this is what you see. Make that a little bit bigger. Over here you have your specifications that you can change. So you first specify your properties and then your simulation conditions. Up at the top there's a number of resources, including Dipper, links to Dipper and other property packages or drawing structures. The first step is to enter in our water and air components. So you click on the half full pessimistic red label. That's very helpful to let you know what you need to do. So first we specify components. So let's do find, and let's say equal. So there's quite a few components in here. Click air, find, or just an enter, add selected component, and then we'll enter our water. Enter, and there's our water. Add that as well. Don't replace the water or air, just add the water. Close that and you can see our two scenarios here. The next step is to enter the methods. So what specifically, how do these molecules interact with themselves and with each other? And in this case we'll say they'll interact. Ideally, you can see a number of different packages and treatments here. We won't talk about them, but we'll just use the ideal. Henry's law, coefficients. How does the specific air, in this case, go into the water, and how does the water go into the air? In that case, it's a Raoult's law. We've specified that. Now we can go on to our simulation. Here we can choose a unit operation. You have mixers, separators, exchangers, columns, etc. Here we're going to use a separator, and we're going to use a flash drum. It has a 2-outlet flash. So there's one outlet is the vapor, one outlet is the liquid. Just click and drag that up there. And then you notice the half full things here. What do we need to specify? So first, we'll specify our flow sheet and global. And global indicates the entire simulation. In this case, we have a B1 flash model, and we want to specify the flows, inlet stream. So let's say water in, and we also want dry air in, and then our outlet will be vapor out, and we're limited to 8 characters, so we'll do liquid out. And then notice it's popped up a streams folder. Here we're going to specify what is our dry in air flow. Remember, it was 50 C and 1 ATM. So I can click this guy, 1 ATM. And our total flow was 400 kilograms per minute. And we have it's 100% air and 0%. These are actually mass fractions. Or right here, actually molar flow. We're going to say mass fraction. How about that? Mass fraction. 1 and 0. Perfect. Now we want to specify our water flow rate in. Our temperature 50. Our 1 atm. 1 atm. There. Our mass flow. We don't actually know what it is, so let's just guess. Let's say 100. Let's try that. Kilograms per minute. And we'll also specify our mass fractions here. Here we have 0% air, fraction-wise. Mass fraction of 1 for the water, as this is our water inflow. And notice now we have check marks by the stream, and then we also need to designate what are the conditions inside of the flash drum. So let's click right here on our inputs. So we got temperature 50 and pressure of 1 atm. We can have vapor and liquid phases. And now we're good to go. We can simulate the simulation, play it, run it, hit the run button. And right now it's calculating what the equilibrium values for the liquid out and vapor out. So it just completed. Now we have liquid out. What do we have? Results. We'll click on that. There's our results for that. You can see the mass flow rate is, let's change these units to kilograms per minute, 65. So approximately 34 kilograms per minute of water went into the vapor phase. So if you click back on here for vapor, our results, you can see the mass flow, kilogram per minute. So yeah, around 34 added to that 400 amount. So let's see what our relative humidity is of this stream. You can add a property and say relative humidity. Say okay. I think it's, where is it? Right here, relative humidity, 99.9%. So it's basically saturated practically at 50 C with the water. And our mole fractions, our mass fractions of this vapor stream, 92% air and 7.9% water. And our mass flows for each in kilograms per minute are right there. So that's an example of how you can simulate a scenario that's right here. Obviously, you could change the flow rate of the liquid, that water in, to check your answer from your mass balance equations as far as what the flow rate of water into the air would be. Thank you so much.